In this video we're going to talk about Unit 6, Objective 1, continuity at a point. So continuity is just if a function is continuous or not. So back in Algebra 2 pre-cal, we talked about continuous functions being functions that you can draw the entire graph of without picking up your pencil. So if we had a function that looked like that, that's continuous because we can draw the entire function without having to pick up our pencil. In calculus, we are really only concerned about if a function is continuous at a certain point, not over the entire graph. So instead of looking at the entire graph, we'll look at, say, some point C, and we're going to have to decide, is the graph continuous at that point C? So for calculus purposes, continuity at a point is defined as follows. So, continuity at a point. A graph is continuous at point C if the following thing is true. The limit as x approaches that point C of f of x is equal to the y value at that point C. So limit as x approaches C of f of x equals f of C. One thing that you do need to be careful about is this right here implies the fact that the limit as x approaches C from the left of f of x is equal to the limit as x approaches C from the right. So the limit from the left and the limit from the right have to equal each other. So if we're looking at the little graph that I drew up here, let's go ahead and call this value right here f of C. So the limit coming in from the left-hand side and the right-hand side both meet at the value f of C, and the actual y value is f of C, so that's going to be continuous. How you might see this, a real basic way you might see this, is you could have a problem that looks like this. So let f of x equal the piecewise function x squared plus 4x plus 3 over x plus 1 when x is not equal to negative 1. And then let your function be 2 when x equals negative 1. And you might be asked to prove that f of x is continuous at x equals 1. I'm sorry, negative 1. So we need to think about our limit here. Does the limit exist? So if we think about the limit as x approaches negative 1 of x squared plus 4x plus 3 over x plus 1. So if we're trying to think about the limit, as x approaches negative 1, we want to think about what's happening on the left-hand side and the right-hand side of negative 1. We don't really care what happens at negative 1, so that's why we want to take this function part, because if we look at the function definition up here, that function, the x squared plus 4x plus 3 over x plus 1, is going to be everywhere except x equals negative 1. So on each side as close to negative 1 as we can get. So if we plug negative 1 in, we're going to get negative 4 plus 4, which is 0, over negative 1. So we get 0 over 0, so we can think about L'Hopital's rule. So we think about the limits, take your derivative, plug in negative 1 again, and our limit is going to be 2. So we know the limit as x approaches negative 1 of f of x is equal to 2. By the limit definition, that limit has to be the same thing as f of negative 1. So if we look at how our function is defined, when x is negative 1, our function is 2. So since both of those things equal to our function is continuous. So therefore f of x is continuous at x equals -1. So that's how we show something is continuous. There are 4 types of discontinuities that we need to talk about, 3 of which will probably show up in some way, shape, or form, and the 4th one we don't really have to worry about too much. So the first type of discontinuity is going to be what we call a removable discontinuity. But you are probably more familiar with them as just a hole in the graph. So a removable discontinuity or a hole. If you remember from pre-cal, these are going to happen when you can divide out a factor from your denominator. So you can divide a factor out of the denominator. So remember, our discontinuities are going to happen when our denominator is 0. If we can factor it out, cancel it away, it's going to be a hole. What this will look like in calculus is the limit as x approaches your value c of f of x is going to exist, but it's not going to be equal to the function value at f of c. So an example would be if we take that same function we just dealt with and say x squared, so f of x is the piecewise function x squared plus 4x plus 3 over x plus 1 when x does not equal -1, and let's change it to 4 when x does equal 1. So if you take the limit, we know from the last slide that the limit as x approaches -1 of f of x is going to be 2. But if we look at how we've defined this function now, we know that f of -1 equals 4. So the limit exists, but the function value is not there. So if you were to look at a graph of this, our graph would look like this, where this is the x value -1, and we would have a hole at 2, and then a closed-in circle above it at 4. So if you were thinking about drawing this without picking up your pencil, you wouldn't be able to do so. So that's going to be a removable discontinuity, and as far as calculus goes, you're going to be looking for your limit existing but not being equal to your function value. The second type of discontinuity is going to be a jump discontinuity. And this one is not going to be dependent upon a 0 in our denominator. This one's going to happen exclusively with piecewise functions. What the calculus will look like is the limit from the left of f of x, so left of c of f of x, is not equal to the limit as x approaches c from the right of f of x. So an example of that might be something like f of x is equal to x plus 7 if x is, say, less than 4, and negative x if x is greater than or equal to 4. So if we take our limits, the limit as x approaches 4 from the left of f of x would be using the top piece of that piecewise function, so we're going to get 11. If we take the limit as x approaches 4 from the right of f of x, we're going to be using that bottom piece, and we're going to get -4. So if you think about a graph, at the value x equals 4, so I'm just going to say that this is 11, and that's -4. Our graph is going to look like this. So you can see that there's a big jump. Coming in from the left, we're going up to the y value of 11. Coming in from the right, we're going to the y value of -4. So there's that big gap right here, and that's why you can see it's a jump discontinuity. So we're looking for our limits to not match. The third type, and we've kind of talked about these already, is going to be an infinite discontinuity. And that's just a vertical asymptote. And you find those when you have a 0 in the denominator that does not cancel out. So that doesn't change from pre-cal. If you are thinking about your calculus, this would be the limit as x approaches c from the left of f of x is going to be equal to positive or negative infinity. The limit as x approaches c from the right of f of x would also equal positive or negative infinity. They don't have to be the same. They could, but they don't have to. So if we look at a problem, we can say f of x equals x over x plus 3. And we could ask if we are continuous at the point x equals -3. So based on what you did in pre-cal, you can clearly see that a -3 is going to give us a 0 in the denominator. We can't cancel it out, so we know right now that we have a vertical asymptote at x equals -3. But if you wanted to show it, we could say the limit as x approaches -3 from the left of f of x would be a point just a little bit to the left of -3, so something like -3.000, a whole bunch of zeros, 1, and then -3.000, same amount as zeros, 1, plus 3. It's going to give us that number, which I don't have room on the screen to write, over 0.000, whole bunch of zeros, 1. Both of those would be negative. So we're going to go to positive infinity. You could do the same thing with -3 from the right-hand side. But we've talked about those ones already. You're not really going to ever have to show them. You just have to recognize them like you did in pre-cal. All right, running out of time. Last one that you're not going to have to really do anything with. I didn't number any of the other ones, so let's get rid of the number. The last one, the fourth type, is called oscillating discontinuity. And there's not really any calculus to show you about it. And that's okay because you're not really going to have to ever do anything with an oscillating function. But what an oscillating function looks like, you'll have a nice controlled curve until you get to a certain spot, and then it's just going to go oscillate back and forth really quickly, and then it's going to be nice and smooth afterwards as well. And inside all of that quick oscillations, you can't really tell what's going on. Nothing is going to exist there as far as limits, derivatives, any of that type of stuff. That has never been on the AP exam, so you don't really have to worry about that one. So that'll do it for this video. We'll see you in the next one.